remember several years ago I was reading a fascinating book by Weinhold and Landis called Valency and Bonding, where they discuss natural bond orbitals. It's a seminal text on hybridization theory. If you want to know more about hybridization theory, we've done a few videos now, which we can put in the show notes. I was going home and carrying the book with me instead of putting it in my backpack, mostly because it's a pretty hefty volume and my backpack was heavy enough as it was. I went to get on the elevator in our parking garage, and one of my physics colleagues got on with me. He said, "There's that much to study about valency and bonding?" I just looked at him and smiled and said, "Oh yeah." Famous chemist Robert Mulliken once said, "I believe the chemical bond is not so simple as some people seem to think." You remember this photo from a previous video on MO theory? Mulliken is third from the right, and he is there with a few names you may recognize like Werner Heisenberg and Paul Dirac and Hund. Mulliken won a Nobel Prize in chemistry in 1966. Charles Coulson, a mathematician and chemist who made important contributions to both MO theory and valence bond theory, said of Mulliken's quote that it ought to go down to history as one of the most classic understatements of all time. By the way, Coulson had some famous students that worked for him with names you might recognize, like Peter Higgs. Today, we'll talk about maybe the simplest kind of bond, the two-center two-electron bond. We'll talk about one way of thinking of the bonding you may have never seen that is based on hybridization theory. It's called the theory of polar covalence, and it allows you to calculate the energies of bonds with the numbers from a table and a few simple equations with an accuracy that suggests it has something fairly deep to say about the nature of bonds. We'll assume you know the concepts behind electronegativity, particularly Sanderson electronegativity, at some depth, and we have a video on that linked in the description. In that video, we mentioned polar covalence theory, and that a video on that would come later. Well, now is later, I guess. One thing I'll remind you of right now, Sanderson electronegativity is just based on the ratio between the electron density of the atom and an ideal electron density that Sanderson thought was related to the noble gases. That's it. No bond energies go into making Sanderson electronegativity, unlike Pauling electronegativity. The idea here is pretty simple. We'll use just two resonance forms to describe a two-center two-electron bond between atoms A and X. We can equally share the electrons in the bond, like on the left, or we can polarize the bond, like on the right. In this case, we'll assume that X is more electronegative than A, so that the other possible polar form, A minus X plus, doesn't contribute. The bond energy for AX is then this, where the E sub C is the covalent bond energy, E sub I is the ionic bond energy, and the two T's are coefficients describing how much the ionic and covalent forms contribute. Since we are assuming these are the only two resonance forms, the sum of the two T's is 100%, or 1 equals Tc plus Ti. The covalent bond energy was calculated similar to how Pauling did it in his electronegativity scheme, if you remember that. But Sanderson added a correction factor for the bond distance and a factor taking the bond order into account. The equation looks like this, where R sub C is the covalent bond distance calculated from covalent bond radii for the single bond, R sub 0 is the actual bond distance, beta is a constant based on the bond order, and E sub AA is the covalent homolytic bond energy in A, like when A is bound to itself. Notice that the correction factor for the bond distance, RC over R naught, gets larger as the bond gets shorter than a single bond. In other words, if the bond is shorter than expected, it makes the covalent part of the bond energy higher. If the bond is stretched for some reason, for example, maybe the atoms can't get as close as would be ideal due to sterics, then it weakens the bond. Outside of the correction values, the equation is taking the geometric mean of the homolytic bond energies of the different atoms in the bond. In other words, the assertion is that the covalent part of the bond is a mean of the intrinsic covalent bond energies associated with the atoms. The AA bond is purely covalent, and that will contribute a set amount when A bonds to anything. That's the idea. A constant beta is tabulated here. For a single bond, beta equals 1, so you can ignore the value for single bonds. As you may know, a double bond isn't twice as strong as a single bond, etc., so it's not a surprise that double isn't 2 and triple isn't 3. It's a bit more complicated than polar covalence saying that a double bond is 1.48 times as strong as a single bond, because the bond distance also changes the covalent bond energy, not to mention the ionic bond energy. However, Across many compounds, Sanderson found beta to be the constant shown after taking all this into account. The compound you're looking at is purely covalent. You can calculate the bond energies now, like in dinitrogen. This equation just becomes E sub N2 equals TCEC because there is no ionic part when the atom binds to itself. Further, the Tc equals 1, so the bond energy equals the covalent bond energy. The equation we need is this one, and we need a few values. First off, you need beta equals 1.787 for the triple bond in N2. The covalent bond radius of nitrogen is 0.734 angstroms, so the single bond distance is twice that at 1.468 angstroms. The actual bond distance in N2 from experiment to 3 significant figures is 1.10 angstroms, and the N in covalent single bond energy is 94.9 kcals per mole. If you put all that into the equation, you get 226 kcals per mole for the bond energy in N2. The experimental value for the bond energy is 225.9 kcals per mole. So polar covalence theory is dead on for this simple calculation. If the compound you're looking at isn't purely covalent, you need to calculate the ionic bond energy, E sub I. The energy of the bond here literally just comes from Coulomb's law. You might be more familiar with the force version. The R hat is the unit vector running between the two charges to give the force a direction. The R squared is the distance between the charges squared, and Q1 and Q2 are the charges. The epsilon naught is the constant called the permittivity of a vacuum, which is related to how well electric fields move through a vacuum. Instead of the force, we can think of the work required to put the system together, the potential energy U that is required by the system with a specific configuration of the charges. That's defined using this equation, which is really only different from the force in that it isn't a vector. It's just an energy, and it is dependent upon the distance r instead of the distance squared. If we plug in that the charges are +1 and -1, like in our polarized structure, and we put in the unit charge, Q equals 1.602 times 10 to the negative 19 ampere seconds, which is called the Coulomb, and we can put in the value for epsilon naught, we get this equation. This simplifies to this. 1 joule of energy is defined as 1 kilogram meters squared per second squared, so the numerator is in joules times meters. Hopefully, you'll forgive me for liking bond energies in kcals per mole. I like these units better than kilojoules per mole because a CH bond is then about 100 kcals per mole. CC bonds are around 80 kcals per mole, and a strong hydrogen bond is about 10. If you'd rather work in kilojoules per mole, just multiply by 4.184. To convert the equation above to kcals per mole, we multiply by 2.39 times 10 to the minus 4, and by Avogadro's number, 6.022 times 10 to the 23rd per mole. Here, the expression is in meters, and bonds are typically a pretty small fraction of a meter. The typical unit I'll use is called the angstrom, which is just 1 times 10 to the minus 10 meters. Typical bond distances are in the order of 1 to maybe 2.5 angstroms. The other thing we'll realize is that the potential is the energy required to assemble the system. What we want is the energy required to break the bond, tear the system up. So we just change the sign. The ionic bond energy is just 332 divided by the bond distance in angstroms, which gives the bond energy in kcals per mole. Just like in the covalent bond energy case, we multiply by a factor beta for bond multiplicity, and beta equals 1 for a single bond. If we look back at our equation for bond energy, we have expressions for E sub C and E sub I now. We only need to calculate the T coefficients, and we can calculate the bond energies. Of course, the T's are related, 1 equals Tc plus Ti, so we really only need one or the other. Sanderson developed a method to calculate the charges in a molecule to find the Tc value. You can estimate Tc by the equation here, which is the average partial charge across the bond. Basically, if the charges were +1 and -1, then the bond would be completely ionic. So Ti would be equal to 1 and Tc would be equal to 0. If the charges are less than 1, then there is some covalent character. The equation to calculate the charge delta of an atom in a molecule looks like this, where chi A is the Sanderson electronegativity of the atom you're calculating the charge of, and chi M is the molecular electronegativity, and delta chi A is the change in electronegativity of A with unit charge, which Sanderson found empirically to be 1.57 times the square root of chi A. The molecular electronegativity is the geometric mean of all the electronegativities of all the atoms in the molecule. For our AX system, it would be the square root of the electronegativity of A times the electronegativity of X. The general equation for any system would look something like this, where n is the number of atoms in the molecule, and you're taking the nth root, and Na would be the number of atoms of A in the molecule, and so on. Those are all the equations you need to calculate the bond energies. Here's a table summarizing all of them in one place. I know it looks like a lot, but it's actually pretty simple. You can do this in a couple of minutes for most molecules. Let's do an example. Let's calculate the bond energy of the TiCl bond in titanium tetrachloride. It's affectionately known as TiCl4, and it's probably the most common starting material in titanium chemistry. TiCl4 is a colorless liquid when it's pure, and you need to tabulate some values for titanium and chlorine. And additionally, you need the TiCl bond distance in TiCl4. You can assume that it will be about the sum of the covalent radii, in which case Rc over R naught is 1 and can be ignored, but the experimental value is R naught equals 2.170 angstroms from electron diffraction. So let's see what we find. Let's start with the covalent bond energy. The TiCl bond is a single bond, so beta is equal to 1. Rc is equal to 1.65 plus 0.994 equals 2.644 angstroms. So for chlorine, you'll see three different values for the homolytic bond energy: fully unweakened, partially weakened, and fully weakened. You'll notice that atoms that typically have lone pairs have three values, and Sanderson called the effect lone pair bond weakening. He didn't know what the effect was due to. I do, because some brilliant folks have figured it out over the years, but I need a whole other video to tell you about it, so I'll just tell you that you need the fully unweakened value here, 71.8 kcals per mole. So the equation is just this. The ionic bond energy is even simpler to calculate. Notice how much larger the ionic bond energy is than the covalent, over twice as large. Generally speaking, for similar systems, more ionic bonds are stronger, and you can see why. Now, all we need to do is calculate the coefficient Ti, which we do from the charges. First, we need the molecular electronegativity. This is the fifth root of the electronegativity of titanium-4 times the electronegativity of chlorine to the fourth power, because there are 4 chlorines. Notice that the electronegativity of titanium goes up with the formal oxidation state, just as you would expect. Then we can calculate the charge on titanium. Electronegativity doesn't have units, but the units on the delta chi Ti values can be thought of as electronegativity per unit charge. On top, we have the molecular electronegativity, the average everywhere in the molecule, versus the electronegativity of titanium. Titanium is less electronegative than the mean, so it gives up electron density and will be positively charged. The bigger the difference, the more charge it gives up until it gives up a full cationic charge at 1.923 in difference. The difference is smaller than that, and the charge on titanium is positive 0.748. There are 4 chlorines and only 1 titanium, and the molecule is neutral overall, so the chlorine should have a negative charge that is 1/4 of the size of the titanium and negative. So it all cancels out. So negative 0.748 divided by 4 equals negative 0.187 on each chlorine. We can do that, or we can use the equation below that gives basically the same answer. The estimate for Ti is the average of the absolute values across one of the bonds. So 0.748 plus 0.183 divided by 2 equals 0.466. The Tc value is 1 minus Ti, so Tc equals 1 minus 0.1466 equals 0.534. In other words, the bond is 53% covalent in this case. Now we have every value to calculate the bond energy in TiCl4, which turns out to be 102 kcals per mole. This is the bond energy, which is the average CiCl bond dissociation enthalpy in the compound. An experimental value for TiCl4 equals 102.8 kcals per mole, meaning our calculation has an error of about 1%. Typical errors are within about 5% for this method. A quick note about what this means. The bond energy in something like TiCl4, according to IUPAC, is the average bond enthalpies for all of the equivalent bonds. Another way of thinking about it is the atomization energy divided by the number of bonds. In other words, it's the energy required to completely blow up the molecule and turn it into Ti plus 4 chlorine atoms divided by 4 bonds in this case. There's something different called the bond dissociation enthalpy, which is the enthalpy, which is approximately heat, required to homolytically cleave a bond. So something like this, TiCl4 going to TiCl3 plus chlorine. Of course, you can do all the bonds in TiCl4, then divide by 4 bonds, which is the bond energy again. What does all of this teach us? Number 1, just using 2 resonance forms, we can understand bond energies. Number 2, the covalent part of the bond is related to some inherent property of the atom. Number 3, the polar part is related to just the bond distance. Number 4, the charge of an atom in a molecule is related to the electronegativity of the atom relative to the molecular electronegativity. Number 5, the polar resonance form has much higher energy in most cases. So in similar systems, more polar bonds are stronger. So what are some of the limitations of polar covalence theory? It only works for covalent systems. Dative bonds don't work the same way, and the same resonance forms aren't applicable. It works well for binary systems, things comprised of only 2 types of atoms, and may fail for others. The reason it fails is the charge scheme. If you have 2 of the same atoms in different environments, then the charge scheme says that they will have the same charge, which obviously isn't always correct. It's just that the charge scheme isn't sophisticated enough for the cases like this. So, for example, if you have 1,1,1 trifluoroethane, which is the R143A refrigerant, and want to calculate the CC bond strength, you run into an issue. Namely that the carbon with all the fluorines on it should be more positively charged than the carbon with the hydrogens on it. That just seems obvious from the electronegativities. However, Sanderson's simple charge scheme just doesn't account for the different environments and says that both carbons will have the same charge. In other words, it doesn't take into account the geometry in every trifluoroethane, regardless of whether it's 1,1,1 or 1,1,2, will have the same calculated charge on both carbons. Why is this important? It's important because one of the things we just learned is that for similar systems, polar bonds are stronger. Let's consider a very interesting reaction reported by Jerry Mills and coworkers in 1989. It involves the reaction of a compound with a phosphorus-phosphorus bond with electronegative CF3 groups with a related compound with a PP bond that is just methyl groups. We could try to use Sanderson's method to calculate the bond energies here for all 3 species to find out if this reaction will go forward, but maybe you see the problem already. In the mixed compound on the right, listed as the product, the 2 phosphorus atoms are in different environments, so the simple Sanderson charge scheme will erroneously give us the same charge for both. However, because one of the phosphorus atoms has electronegative CF3 groups, and the other has methyl groups, there will be polarity in the Me2PPCF32 compound that is not in either of the starting materials. In other words, these are 3 different compounds with different bonding. Only the compounds on the right have any ionic character to the phosphorus-phosphorus bonds. We know from the discussion above that all other things being equal, more ionic bonds are stronger. As a result, we predict that the reaction will proceed to the right. What we found experimentally is that the reaction goes all the way to completion to make the mixed compound. Again, I like Sanderson's polar covalence theory. You can use it to get bond energies pretty quickly using simple math. I think more importantly, it really teaches something about the fundamentals of bonding. Bonds can have covalent and ionic forces at play, and this is built into the method. Another very important effect that comes out of the method is lone pair bond weakening, and that can be used to explain a lot of interesting chemistry, but it is also a story for another video. Thanks for watching this introduction to polar covalence theory. We make these videos for fun and to give back to the community. Please subscribe, give us a thumbs up, and take a look at the rest of our playlist, which has videos at a variety of levels. Hit notifications so you don't miss anything, because we drop videos only occasionally. Thanks.